Hello everyone. Today we'll be discussing continued part of concept of resonance in series RLC circuit. In last class, we discussed about the basic concept of AC circuit, how voltage and currents are related for series RLC circuits for different parameters such as inductor, capacitor, and resistor, how voltage and current are behaving, what's the phase angle between these two, how phasor diagram can be drawn for individual elements. Later, those concepts are together to discuss about series RLC circuit, concept of series RLC circuit, how voltage and current behaves in series RLC circuit, what is impedance triangle that we discussed. Later, with that concept, we moved towards the concept of series resonance, and we discussed what happens at resonance, how impedance becomes minimum, current becomes maximum, all those being discussed in last class. Now today, based on the fact of series resonance, we'll be discussing about some graphical representation of different parameters such as variation of inductive reactance, capacitive reactance, current, impedance with frequency that we'll be discussing today. So let us start with the topics to be covered. Today we'll be discussing about how R, XL, XC, Z, I, all these varies with frequency. Along with this, we'll be discussing about variation of phase angle with frequency as well. Next, we'll discuss about bandwidth and half power frequency. So let us start with the basic concept of series resonance, which earlier we discussed in last class. So let us recapitulate this part once. At series resonance, as we discussed, the inductive reactance should be equals to capacitive reactance. So net reactance at resonance should be 0. So the circuit must behave as a purely resistive circuit. If this part becomes 0, then the circuit will behave as purely resistive circuit. At purely resistive circuit, as the circuit behaves as purely resistive circuit, so Z will become equals to R, which implies the minimum value of impedance at resonance is offered by the circuit. Consequently, maximum current will be there. At resonance, as the circuit behaves as purely resistive one, so the phase angle between voltage and current will be 0 degree. That means voltage and current will be in same phase. Power factor will become unity. So as power factor becomes unity, the maximum power will be delivered to the load side. So these are the basic concepts of resonance which we discussed earlier. Now let us today discuss its graphical representation and the derivation of resonant frequency as well. Okay. Let us denote resonant frequency by FR. Now, this formula is well known to us. XL equals to omega L, where omega is angular frequency. So the formula for angular frequency is 2 pi f. Now at resonance, the frequency is FR, that is resonant frequency. So at resonance, XL will become equals to 2 pi FR into L. Similarly, XC will become equals to 1 by omega C, that is 1 by 2 pi FR into C. Since at resonance, XL and XC should be equal, so 2 pi FRL must be equal to 1 by 2 pi FRC. This will lead to this equation. So this is known as resonant frequency. So the formula for resonant frequency is FR equals to 1 by 2 pi under root LC. So if inductance value and capacitance values are known to us, we can select the resonant frequency for that particular circuit. So this equation implies resonant frequency is independent of resistance. It only depends on L and C values. Consequently, FR omega, that is angular resonant frequency, will be 1 by under LC. So this is the derivation of resonant frequency. Now, how inductive reactance and capacitive reactance varies with resonant frequency. See, We all know XL equals to 2 pi FL and XC equals to 1 by 2 pi FC. Now, if frequency increases, suppose frequency is, let us assume this, frequency is 0, 1, 2. Suppose we have taken 5 frequencies. This is not the actual case. For example, we can consider this. Now, XL equals to 2 pi FL. So, from this equation, we can say XL varies with frequency linearly. So, this is variation of XL with frequency axis. Clear? X equals to 1 by 2 pi FC. So, this should be the variation of XC with frequency. So, based on these two formulas, we can draw this graphs which shows the variation of XL and XC with frequency. Now, numerically, at 0 frequency, XL 0, and it is very high. X is very high, infinite almost. As frequency increases, say this is 2, say this is 10. At 2 frequencies, say this is 4, this is 7. At 3 frequencies, say this is 5. And this is also 5. At 4 frequency, say this is 7. This is 3. At 5 frequency, say this is 10. This is 1. Likewise. So what can we conclude from this? As frequency increases, if frequency is 0, XL will become 0. If frequency is 1, then XL will have some certain value, XL will be increasing with frequency. Similarly, XC will be decreasing with increase in frequency. At a certain frequency, see here, both inductive reactance and capacitive reactance, XL and XC, are equal, which implies the net reactance of the circuit at, as shown here, at frequency 3 Hz will become 0. So this is the frequency at which resonance will occur, as these two reactances are equal. So this is how we can show variation of XL and XC with frequency. Now, why this is written? See, for this region, let us omit this part. For this region, this part, which one is greater? XC is greater. So at the initial part, from 0 to resonant frequency, XC is greater than this XL. Okay. See here, till resonance, which one is greater? XL is 0 to 4, X is infinite 10, 7. So till resonance, XC is greater than XL. This implies, what does this imply? This implies that at resonance, before resonance, the capacitive reactance will be more than inductive reactance, so XC is greater than XL. So the net reactance will be capacitive type, and the circuit will behave as a capacitive circuit. But after resonance, which one is greater? XL is greater than XC. See, this green part of the table shows after resonance, the XL is greater than XC. So this implies the circuit behaves as inductive circuit. But at resonance, as these two XC and XL meet at certain point, when XC is decreasing and XL is increasing with increase in frequency, at a particular frequency, these two will meet at a point. That frequency is known as resonant frequency. So at this frequency, resonance will occur when XL will become XC. So, so the circuit at this point will behave as purely resistive circuit. Clear? So this is the variation of XL and XC with respect to frequency. Now, how impedance Z varies with frequency? This is formula for impedance. Now, say this is frequency, this is Z. Suppose R equals to 10, R equals to 1 ohm. Before resonance, as we discussed earlier, before resonance, XC is more than XL. Okay, so this is XL. Suppose with variation in frequency, this XL and XC varies like this. So see, at frequency 3, resonance will occur. Okay. Now what is Z? Z is under root R square plus XL minus XC whole square. So how this XL minus XC part varies? See, initially this difference is 9. Then this difference becomes 4. Then this difference becomes 0. Then this difference becomes 2. Then this difference becomes 4. So what is happening here? Till resonance, during this part, till resonance, XL minus XC, this part is very large. Which one is greater? XC is greater. So XL minus XC becomes minus 9, minus 8. So as it is whole square part, so minus 9, minus 8, this minus will have no effect on whole square. So till resonance, from 0 to resonance, the difference is decreasing. First difference is 9, then difference is 4. So till resonance, difference is decreasing. So as this difference is decreasing, for a constant R, Z will be decreasing first. So initially Z is, say, initially Z is 10. Then Z is 7. At resonance, Z will be equals to R, that is 1. Again, after resonance, for this part, after resonance, what happens? Again, it is increasing. This Z is increasing. See here, 4 minus 2, 2, 5 minus 1, 4. So 2 to 4. So it is increasing. Say this is 5. This again becomes 7. This again. So what is happening here? Initially, till resonance, impedance is decreasing. Then after resonance, impedance is increasing. So Till resonance, impedance is decreasing. After resonance, impedance will be increasing. Till resonance, Xc is greater than XL. So this part will behave as capacitive. After resonance, XL is greater than Xc. So this part will behave as inductive. So this is how you can conclude an impedance curve in which impedance varies with frequency. So at this point, see, impedance becomes minimum when XL becomes equals to XC, impedance is equals to R. So this magnitude is denoted by R. So this R is known as dynamic impedance. This is the lowest impedance offered by a resonating network when at resonance. So this is known as dynamic impedance. Now how current behaves? See, for a constant voltage, as impedance, what was the impedance curve? Impedance curve with frequency was like this. So as impedance is decreasing till resonant frequency. So till resonant frequency, current will be increasing because current and impedance are reciprocal to each other. Then again, it is increasing, impedance is increasing, so current is decreasing. Okay. Now, see, this is an important point. As we are frequently talking about net reactance becomes zero at resonance as XL equals to XC, or voltage drop across L and voltage drop across C are equal. So at resonance, these two parts together will have no effect on circuit. XL minus XC at resonance, XL equals to XC, or XL minus XC equals to 0. So what is XL, what is XC? XL is inductive reactance, XC is capacitive reactance. Or we can say XL is the resistance offered by inductor, XC is resistance offered by the capacitor. So these two elements, these two reactive elements together offer no resistance to the network at resonance. So as these are offering no resistance to the network at resonance, so these two should act as a short circuit. That is why it is shown here. At resonance, L and C together will act as a short circuit. Now, how phase angle varies at frequency with frequency? See, what we discussed till now is XL and XC varies with frequency. Now, as frequency varies, frequency increases, there is resonant frequency, then again it varies. So this part from 0 to FR, from 0 frequency to FR frequency, XC greater than XL, that we discussed earlier. And for this part, XL greater than XC. Clear? Now, when XC greater than XL, the circuit behaves as capacitive. So if this is I, then the capacitive part, XL minus XC part will be, this will be the voltage part, and VR will be acting in this direction, voltage across resistor. So what is resultant? This would be the resultant. Okay, resultant voltage. So, sorry. For capacitive part, this will be VLC, voltage across LC, because for capacitive part, the current leads. So this will be the resultant V if this is VR. So current leads the voltage. So here see, this is the current. So current leads the voltage by an angle theta. So till resonance, as circuit behaves as capacitive, so current will lead, voltage will lag. So as current leads, so we can get this phase angle. Why? We know tan phi equals to XL minus XC by R. As XC is more during this part, so tan phi will be negative. So negative phase angle will get at resonance. The Z equals to R and XL equals to XC. So tan phi at resonance, tan phi equals to XL minus XC by R, which is equals to 0, as XL equals to XC. So phi is 0 degree. So at resonance, phi is 0 degree. Again, after resonance, as frequency increases, the circuit becomes inductive and your phase angle will be positive. As XL becomes more, so phi will be positive. So this is how with frequency phase angle varies. Now, what's the effect of resistance on resonating curve? At resonance, Z equals to R. If this R increases, then I will be decreasing if R increases. Okay. Now, so this is having small r. If R is small, then I will be large. If R is medium, this will be a I, maximum current at resonance. For high R, this will be lesser I. So the resonance curve becomes sharper with small resistance. Now, what is the concept of bandwidth? See, this is Imax, current at resonance, which is maximum. And this is 0.707 of Imax. Okay. What is 0.707 of Imax? That is Imax by root 2. Okay. Now, what is formula for power? P equals to I square R. Now, at resonance, power will be Im square R. As at resonance, power current is flowing Im. But at this point, at this frequency, which is denoted by FL, at this frequency, current is Im by root 2. So what would be power? This will be power at resonance, at this frequency at FL frequency, which will be half of Im square R, if it is PM, half of PM. So at this frequency, at FL frequency, the power becomes half of the power at resonance. So this frequency point is thus known as half power frequency point. Similarly, again at this point, current is Im by root 2. So consequently, this is another half power frequency point. So this is lower half power frequency point. This is upper half power frequency point. Okay. Or simply it could be termed as lower frequency or upper frequency. Average of lower frequency and upper frequency will give us resonant frequency. Now, these are what about half power frequencies. Now, the difference between lower frequency and upper frequency is known as bandwidth. So bandwidth, the band of frequency for which the current to the circuit becomes Im by root 2 or more. Okay. This is known as bandwidth. So whatever is discussed, this is written here. This is the formula for half power frequency, which depends on R and L and C, all these parameters. This is low, upper half power frequency. So for lower half power frequency and upper half power frequency, this is the negative part, this is positive part. And FR will be R by 4L. Now formula for bandwidth is FR by Q, where Q is quality factor. What is quality factor? That you already have studied in AC circuits. Bandwidth can also be written as FR minus FH minus FL, which is equals to R by L or R by 2 pi L in Hertz. The quality factor is omega RL by R, which decides the quality of the coil, which is equals to XL by R or 1 by omega R CR. So these are the formulas of quality factor and bandwidth. So these formulas later will be used to solve numericals on resonance. So as of now, today I am ending up here. So what we discussed, let me first summarize all those. We discussed about different graphical representation, how XL, XC, Z, phase angle, I, all this varies with frequency. What are the interpretation from graph that we also discussed? What is resonant frequency? How to derive the equation for resonant frequency? What is half power frequencies, bandwidth, quality factor? All this being discussed in today's class. In next class, we'll be discussing about parallel resonance, and we'll be solving some numericals on series resonance and parallel resonance. So thank you all. Meet you in next class.